Hello dear students, welcome to the channel and welcome back to this playlist in which we are discussing about the symmetrical and unsymmetrical faults in power system. We are also considering the symmetrical components in it, and recently from few lectures now on we have started discussing about the symmetrical components. And in very last lecture, previous lecture, we have discussed about positive positive phase sequence, negative phase sequence, and zeroth phase sequence. And then we also discussed about the symmetrical components of unsymmetrical phasors. In that we have derived the equation for voltages, and the same can be derived for the current as well. And today we are going to discuss about the phase shift of symmetrical components in star delta transformer bank. So generally whenever we consider about positive sequence, the phase shift which occur in the positive sequence and even in negative sequence for any voltages of currents will be through a phase shift, right? For any voltage or current, or for any positive or negative sequence, whenever my any quantity in any sequence going through a star delta transformer, there will be a phase shift, definite phase shift, right? It doesn't matter if it is star delta or delta star, there will be a phase shift, and the phase shift will be around 30 degrees for both star delta and delta star. Okay, so what we have to see here, firstly let's see this figure, which is showing a single phase transformer with polarity markings. Here the dot conventions are representing the polarity of given side of transformer. So the transformers which are transformers ends are marked with say, dots which are having same polarity. So that means this voltage V11 dash and V22 dash are having same polarity. Okay, so now for this transformer, if we neglect the small amount of magnetizing current that is present here, and if we only focus on the primary current I1 which is entering from this dotted convention, what will happen? This primary current I1 will cancel the demagnetizing mmf of my secondary current. Okay, I1 is entering, secondary I2 is leaving. So what I1 will do, it will cancel out the ampere turns of secondary current, and because of that the I1 and I2 with the directions are indicated in the diagram, and both of them are in phase. So if the direction of I2 will be reversed, then I1 and I2 will be in opposite phases, right? I1 and I2 will be in different, completely different or opposite phases. So now let's do one thing. Let's consider a star delta transformer, as you can see in this figure here. And what we will do, we will assume that the transformer is excited with positive sequence voltages, and transformer is carrying positive sequence currents. Okay, so the assumption here is that my transformer is completely okay, hence it is getting excited on positive sequence voltages. So first we are considering star delta. So first we are having star, and then it is getting converted to delta. So for whatever polarity is shown here in the first image here, entering and leaving, the phasor diagram will look something like this for this one, on the immediate left. Okay, and based on that we will get a relationship between my voltage at star side and voltage at delta side, and the difference, which I have already told you, that the difference between phase will be 30 degree. So what will happen, the angle, the quantities of star side will lead the delta side quantities by 30 degrees, right? And let's see how is it happening. So here this an1, you can see this an1 or ab1 is the voltage of star side. Okay, doesn't matter if I'm taking phase or sorry, doesn't matter if I'm taking line voltage or phase voltage, because basically I'm going to talk about the angle only here. So magnitude is not does not matter. So you can take either line or phase voltages. So see, this is the voltage of star side, and if this is the voltage of delta side, VAB capital. Sorry, I took the conventions opposite. If this is the voltage on the delta side, no, okay, correct. They were correct. If this is the voltage on star side and this is the voltage on delta side, you can see that the star side quantities are leading the delta side quantity by 30-degree angle. Okay, so what is happening here? The positive sequence line voltages on star side are leading the corresponding voltages on delta side by 30-degree angle. And you can apply the same thing for line to neutral voltages as well. If you will take line to neutral voltages on two sides for each line current, you will find the same result, that the star side is leading the corresponding voltage on delta side by 30-degree angles. Now if the transformer which is getting excited at this polarity, what will happen if we give negative sequence voltage to it, right? So whenever we apply negative sequence voltages, so the current will shift the phase, and the direction of current will get reversed, right? Because we are applying negative sequence. So earlier the direction of current, if it was positive, then the direction of current here will be negative, right? So direction of current will be completely opposite to whatever the direction of current was in the positive sequence. Now the star side quantities will lag the delta side quantities by 30 degrees. Why? Because see, here the left hand side is still remaining same. See, A, B and C we are having. Here as well we had A, B and C. Conventions are also similar, as you can see here, here and here. So same dot conventions are here, but the change is occurring here. See, this sequence was getting followed here. A, then we had B, and then we had C. But here what is happening? See, we are having A here, the B is here, and C is here, right? So what will happen? We are applying negative phase sequence here. So the star side quantities will lag the delta side quantities by 30 degrees here, as you can see in this second phasor. Your star side quantities are lagging the delta side quantities by 30 degrees, right? So same, the conventions will be same as here. This bn2 or bc2, whatever you want to consider, are the star side quantities, and capital bc2 are delta side quantities. So you can see that the delta side quantities are leading the star side quantities by 30-degree angle, right? So that was your phase shift of symmetrical component in star delta transformer mag, because phase shift is something inevitable whenever you use star delta transformer. Either star delta or delta star, there will be some phase shift, because remember when we did delta to star transformation, we saw that detail that your angle is getting changed by 30-degree. So that is inevitable, that will happen. Now let's see power in terms of symmetrical component, what will happen here. uh, Whenever we calculate power for three-phase circuit, we use symmetrical components, okay? And total power the total power in three-phase circuit, and of course I'm talking about the complex power here, you can give it using this formula: S is equals to P plus JQ, or you can say V phase into I phase complex conjugate, okay? I phase conjugate. So for three phase, you can take summation of all three phases, voltage multiplication of voltage current for all three phases. So you can take if your three phases are A, B, C, so you can take S is equals to VA IA star, VB IB star, VIA star plus VB IB star plus VC IC star, right? And what are this VA, VB and VC? So VA, VB and VC are the voltages to neutral, okay? Voltages to neutral. And the currents IA, IB and IC are the currents flowing through the circuit in the three lines, assuming that your star is connected to the system. So what will be the apparent power? So basically apparent power will be, we saw the formula earlier as well in the previous lecture as well, so I'm not going to discuss how did it came from, because we discussed it in the previous lecture. So if you have not checked out previous lecture, you will be seeing the link flashing on the top right hand side corner of the screen, so you can click on it and you can check the previous lecture out. I will assume that you already know that, so we will start with this formula: S is equals to A into Vs transpose, okay, into, it is multiplied into A into Is conjugate. So here we want a transpose and then we want conjugate as well. Transpose for voltages and conjugate for current, right? So we can represent my phase voltage by this formula: phase voltage Vp is equals to A into Vs, and we can take the transpose on both the sides. So transpose of phase voltage will be transpose of A into Vs. So you can write transpose of A into transpose of Vs. So now let's put the values of uh, all three matrices in this equation. So we know what is the value of Vp from last lecture. We know Vp is equals to Va, Vb, Vc, and we are taking transpose of it. We came to know about the value of A in previous lecture. So the value of A will be 111 alpha square alpha into 1, sorry, alpha square alpha 1 and alpha alpha square 1. That is the value of your A. And value of Vs will be Va1, Va2, Va0. So we are having almost similar values, and we are taking transpose of all three of them. And when we take the transpose of them, what we will get? We will get Va, Vb, Vc equal to the transpose of A will become, you already know how we take transpose, right? We are just basically writing it on from the other side. So its transpose will be 1 alpha square alpha, 1 alpha alpha square, 1 1 1, right? So basically we will write this line this way, we will write this column this way and this column this way. So we will convert columns to rows to find the transpose, and we will find the transpose. We can when we find the transpose, we can show the whatever voltage we get, right? VPH. Now that we found the transpose, and because we are doing all this hard work to find the value of S, we already know value of A's transpose, or we already know the value of this term as well. Okay, A into Vs transpose. So now let's work for A into Is complex value. So same way as we found for current, we can do it for voltage. Sorry, same way as we did for voltage, we can do the same for current. So IP conjugate will be A into Is conjugate, or you can separately write it A conjugate into Is conjugate as well. So we know what was the value of IP. IP is IA, IB, IC, right? And we also know what is the value of A. We just wrote it here, so we will write the same values here. And we are also familiar with values of Is, IA1, IA2 and IA0. So we will basically mention it over here, and we will find conjugate of IP, or we call it IP star. Now what we will do, we will replace the values of this IP star and VP star in this formula. So once we replace the value of IP star and VP star, or basically both of these values, what we will get S is equals to, this is the value of my voltage, this is A, so this is transpose of voltage, this is transpose of A. Then we have A conjugate, which is same as A, and then we have I conjugate. Now the interesting thing is, whenever you do the multiplication of both of these values, both of these vectors, this vector and this vector, you will get the diagonal values 3, and except for this diagonal, all the rest of the values will become 0, right? So basically this will become identity matrix, and multiplied with 3 is, it will become identity matrix which is multiplied by 3, and the value of V phase remain as it is, VA1, VA2 and VA0, and the current will be IA1, IA2, IA0 conjugate. And writing this formula a little bit differently, you can find the apparent power S is equals to 3 VA IA star plus basically 3 VA1 IA1 star plus 3 VA2 IA2 star plus 3 VA0 IA0 star. So your apparent power is the sum of power of symmetrical components. You must have figured out till now. This A1 was the sequence for positive, A2 was for negative, and 0 was for zero sequence. So my symmetrical power of S will be apparent power, and apparent power is the sum of power of symmetrical components, all three of them. So what does it indicate? That it indicates that symmetrical components transformation is power invariant. Okay, so the sum of the power of the three system symmetrical component will equal to three phase power. So based on this symmetrical components, you can also determine the three phase power. Now let's come to the sequence impedance network, or sequence impedance. So firstly, we know that power system elements like transmission line, or you whatever you call transformer or generator, synchronous machines, they all have three phase symmetry in common. And because of that, current will be in particular sequence, voltage will be in some particular sequence, right? And it will be passed through these elements, and will produce different quantities in particular sequence accordingly, right? Like voltage drop or anything else. So the element which are possessing some impedance, these elements will possess only self impedance to sequence currents. Okay, so the elements will have some self impedance to sequence current, And because of that, what will happen, each element can be represented by three single phase sequence networks. So there will be three single phase sequence network for each uh, element, right? And sequence networks will be which, positive, negative and zero. We already know that. So these sequence networks are will be interconnected in different ways to represent direct and balanced fault conditions. And from that, what can we do, the sequence current and voltage can be calculated by us, which are then later converted into some actual fault current and voltages, right? So let's see the sequence network of unloaded generator, or you can also call it synchronous machine. So in unloaded condition, what will happen, the synchronous machine will be grounded through the reactor. As you can see, it is grounded through the reactor, and it is having three phase induced EMF. You can see here EA, EB and EC, three phase induced EMF it is having. So whenever the fault will occur at machine terminal, there will be some flow of current. And what will be the flow of current? You can see here IA, IB and IC will be the flow of current here in your lines. So if the fault will involve ground current, then the sum of all three currents will be equal to neutral current based on the Kirchhoff's current law, KCL, right? Because all three currents are moving outside, whereas the neutral current is moving inside, which means IN will be sum of all three currents, right? From neutral to ground currents, right? Which is flowing through this ZN, neutral to ground current. Now, before we begin the analysis of unsymmetrical faults, there is something that we must know, that any equivalent sequence network of machine will have three sequences: positive, negative and zeroth. Now because of winding symmetry, current of any particular sequence will produce some voltage drop of that sequence only. So because of that, the coupling effect will wash out. So the coupling effect between this sequence networks will not exist. Why? Because there is a winding symmetry, right? And because of winding symmetry current, there will be uh, voltage drop will be produced in that. But the catch is the voltage drop will be produced of whatever the symmetry is applying in that particular sequence. Okay, so if it is positive sequence, then induced voltage drop will be of positive sequence only. So speaking of positive sequence, let's talk about positive sequence impedance network a little bit in detail. So we all know that three phase generator has three phase winding, and these windings will be identical and they will be symmetrical, which means their magnitude will be equal, and they will be equally spaced between each other. The angle between two windings will be 120 degrees, and the number of turns on the windings will also be equal. So it can produce sinusoidal EMF, and it can produce that sinusoidal EMF that will also be 120 degree displaced. Okay, so a balanced three phase voltage will imply existence of positive sequence voltage, because what happens, negative phase sequence and zero phase sequence will available in unbalanced system only, right? So if your system is healthy, that means it is showing positive sequence. If your system is showing positive sequence response, that means your system is under healthy conditions. After that, what will happen, the three phase generator will produce only positive sequence voltages, and synchronous machine is designed with symmetrical winding, right? So what it will do, it will induce the EMF of positive sequence only. So there will be no negative or zero sequence voltages produced or induced inside it. and the flow of this only positive sequence current which has been generated, the flow of this current will produce the armature reaction in field, and because of that it will rotate at synchronous speed in the same direction as the rotor is rotating. So with respect to field, the excitation will remain stationary, right? Because the machine will offer and because of that machine will offer direct access reactance, and its value will reduce from subtransient reactance. Like initially we discussed that initially its value will be xd double dash, then it will be xd dash, and then finally it will be xd. So here xd double dash represents the subtransient reactance, xd will represent my transient reactance, and xd dash will represent the transient reactance, and xd will represent my steady state reactance. Okay, so the positive sequence which I discussed about, uh, this positive sequence impedance of my machine will neglect the armature resistance, and it will say that for the first cycle, the subtransient cycle, the value of my positive sequence impedance will be j into xd double dash, which means the positive cycle, which means the first cycle of transient, or you can also call it subtransient. After the first or second cycle, for 3 to 4 cycles, the value of z will be j into xd dash. So here xd dash is still transient reactance, and once we come close to steady state, the value of my positive sequence impedance will become j into xd. Now during the short circuit condition, if my machine will be unloaded, the terminal voltage will constitute positive sequence voltage. But now if the circuit is under loaded condition, then the voltage behind appropriate reactance will constitute the positive sequence voltages, right? So here in this image you can see three-phase model of positive sequence network of synchronous machine, and as you can see that in is equals to 0, and Zn will not appear for positive sequence current because your system is completely balanced. So your system is working currently correctly, so there is no need for it. Okay, now as it is balanced network, it can be represented by single phase network model, right? And this single phase network model can be seen in this image only. So the reference bus for positive sequence network is at the neutral potential, this one, and the neutral is ground potential, and there is no current flowing from my ground to neutral. So you can show the positive sequence voltage of terminal, uh, this VA1, with the equation based on this circuit only. You can say VA1 will be EA minus IA1, which is the current here, into Z1. So VA1 can be shown as VA1 is equals to ES minus Z1 into IA1. So that was your positive sequence impedance in network. Now let's move to the negative sequence impedance in network. So here what will happen when synchronous machine will have a zero negative sequence, it will induce some voltage, and the flow of this negative sequence current in my stator will produce armature reaction in the field, right? So what it will do, it will rotate in the opposite direction. So because of this opposite direction rotation, compared to the phase sequence field I'm talking about, not any opposite direction, but opposite direction compared to positive sequence field, it will rotate, and with respect to rotor, its speed will be double than the synchronous speed, and when it will rotate at the double speed than synchronous speed, so the current at double the stator frequency will be induced in the rotor field as well as in the damper winding as well, right? So the negative sequence mmf will be alternately present with reluctance of both direct and quadrature axis, and because of that what will happen, the rotor surface will be swept over. So in the case of negative sequence impedance, you can give the negative sequence impedance of your machine as the average of both direct and quadrature axes subtransient reactance. So okay, so if you want to find the negative sequence impedance, so try to find the subtransient average value of subtransient reactance of both uh, B and Q axis, and that will be your negative sequence impedance. So these two phases I talked about, D and Q. So they are conversion from ABC into DQ model of my machine, which is a representation of my three phase into two phase for simplicity and calculation part. So this three phase sequence, this negative sequence model and one phase model of synchronous machine, you can see here in this image, both of them. So the reference bus is again at the ground potential, and you can give the negative sequential voltage of terminal A with respect to the reference bus using this formula. Yes, you can see here VA2 is equals to minus IA2 into Z2. So that is the formula for your negative sequence voltage of terminal A with respect to reference bus. Now let's see the zeroth sequence impedance in network. So unlike the positive sequence and negative sequence, we cannot find the zero sequence network or zero sequence impedance in my synchronous machine. Okay, so the flow of my zero sequence current will create 3 mmf, which will be uh, in same time phase, but will be distributed in space by 120 degrees apart. And because of that what will happen, the resultant air gap flux will come to 0. And as my air gap flux is 0, then rotor winding will present zero sequence impedance only to my zero sequence currents. And you can find it in these two given images, that a zero sequence network model on three phase and single phase will what will happen in them. This one is in the three phase base and this one is in the single phase base. So the current which is flowing in my Zn, this Zn same as any other, will be I current flowing in the Zn will be In equal to 3 into Is0. So the zero sequence voltage of terminal with respect to reference bus can be given using these formulas. So Va0 will be equal to minus 3 Zn Ia0 minus Zn Z0 G Ia0. Same ways you can give Va0 is equals to you can take Ia0 common and you can represent this same formula taking Ia0 common. Okay. So this Z0G is the per phase zero sequence impedance of my machine, and the total zero sequence impedance can be given as Z0 is equal to 3 Zn plus Z0G. So we know the value of Zn, we know the value of Z0G. So you can find the value of Z0, and hence the zero sequence voltage of any point with respect to reference bus can be given as Va0 is equals to minus Z0 into Ia0. So basically multiplication of current with your zero sequence impedance, and you can take negative value, so you can find the zero sequence voltage of any point with respect to reference bus. So that was your zero sequence impedance for network. So we now saw impedance networks for both positive, negative and zero sequences. And now we will be moving on towards the sequence impedance of circuit elements. So we have to do the matricular calculations there, and then we can move forward towards the sequence impedance and network of my transformers. So if you have any doubts, queries, or suggestions related to the channel or lecture, you can mention them in the comment section below. Any feedbacks are welcome, and I will try to address your doubts as soon as possible and as quick as possible. So I will be seeing you in the next lecture. Thank you very much for listening, and take care of yourselves. Bye bye.